friends, this is Saurabh. Welcome to another episode of Progressive Coder. It is almost 6:30 in the morning today and pretty calm environment, nice for recording. The weather is also pretty good, not so hot, not so cold. How's the weather at your end, by the way? Today's problem that we are going to discuss is get minimum element from stack. And that's not the hard part, of course. Getting a minimum element from a particular data structure could be quite easy. The hard part here is that we need to do that in constant time complexity, that is order of 1 time complexity. But before we get into the problem, we want to have a general idea of what a stack is all about. A stack, as you all know, is an abstract data type, and the key property of a stack is that it is a LIFO data structure. LIFO stands for last in, first out, which means that the first element to get into the stack will be the last one to get out, and the last element to get into the stack will be the first one to get out. This is the key property of the stack, and any implementation of a stack should support this behavior. So before we go any further, it is pretty important to also visualize the problem that we are going to solve. And to do so, I have an example over here. Let's consider that we have a stack with 4 positions that is having elements 5, 1, 4 and 2. As you can see in the diagram, 5 is of course the top element in the stack, and anytime we have to remove an element or pop an element from the stack, the top element is returned back to the consumer, which is in this case element 5. 2 is the bottom element, which is basically the last element that will be getting out of the stack. Now here in this particular stack, we can straight away see what is the minimum element, and that is the element 1 over here, and we have a marker over here saying that this is a minimum element. Of course we can see it straight away, but in case you want to find this element, how will you go about it? So what we will be doing is we will be checking element 5, keeping a reference minimum element, then we'll be checking the element 1, and even though it is smaller than 5, we will of course mark it as minimum element, but we cannot be sure at this point that this is indeed the minimum element in the complete stack. To verify and confirm, we have to traverse to the end of the stack. We have to check element 4, we have to check element 2, and finally we can confirm that yes, 1 is the minimum element. So this is how a normal operation for finding the minimum element of a stack will work out. And the main concern with this approach is that it has a time complexity of order of n, which is linear time complexity, because we have to traverse through the entire stack. And this is not our goal, of course. What we want to achieve is constant time complexity. Now to solve this problem in constant time complexity, there are a couple of approaches, maybe at least 3 approaches. One of them, as a clue, will not succeed totally, but we are going to discuss it in the next section. Alright, so let's look at approach 1. In this approach, we have an empty stack. The top and bottom element both are empty right now. There's nothing in the stack basically. We also have a special variable to store the minimum value of the stack. And the idea behind this approach is that whenever a client will ask us for the minimum element, we can simply return the value stored in the minimum variable. So let's try to fill this stack. We have a new element coming in, that is 2, and we are going to put it into our stack like so, and we also update the minimum element. So current minimum element in the stack is 2, and also the top and bottom elements are 2. Another element comes in, element 4. We put it into the stack on the top, of course. Minimum element remains unchanged because 2 is still smaller than 4, right? So we don't have to update anything in the minimum element. Another element comes in, element 1. We put it at the top of the stack, and this time we update the minimum element. So the new minimum element is 1, right? Another element comes in, element 5. We put it at the top of the stack, no change to the min element. So at this point, our stack is full with 4 values, and we also know what is the current minimum value in the stack, which is the value 1. Now let's consider a situation where we start popping from the stack. So we pop element 5, we remove it, no change to the min element because still 1 is the min element. We remove 1 as well, we pop element 1 and now we have a problem. So our minimum element is no longer valid. So 1 is no longer the minimum element in our stack. The new min element is 2. However, if we have to update the min element variable, we have to check the remaining stack completely to verify that 2 is indeed the min element. And in this way, we are again going back to the same problem where we have a linear time complexity. So whatever the remaining elements are there, we have to traverse through those elements and find out the new min element and then update our min element variable. And this is again not what we want. So this is the main problem with approach 1. It doesn't work with our overall goal. Alright, so time to look at approach 2. Approach 2 is based on the premise that each element in our stack should know about the current min value in the stack. For this approach to work, each node or element in our stack should have two components. One is the value, the actual value, and one is the min value at that given point of time. Let's see how it works in action. So we are trying to insert a new element into our stack, element 2. We push it into the stack and the current min value associated with it is of course 2 because there's nothing else right now. We push another element, element 4. Top of the stack, the min element is still 2, right? Because 4 is of course greater than 2. So the min element at this given point of time is still 2. Another element comes in, we push that also, element 1 this time, and now the min element at this point is 1 because 1 is less than 2, right? So we have a new min element. Another element comes in, 5, we push it onto the stack and the min element remains unchanged. Now at this point, let's assume the consumer wants to know the min element, right? So we can very easily say that what is the min element by looking at the top element in the stack, which we have access to at all points of time, and we can find out the associated min value, which is 1, right? Constant time. This is done in constant time complexity. We don't need to do any traversals or anything of that sort to find out the min element. So now let's consider what happens when we start popping the elements. So we pop element 5, so the top moves 1 level down and the min element is still the same, of course, 1 because at this point of time in the stack the min element was still 1. So we can very easily say what is the min element if the consumer asks for it. Let's pop another element. So element 1 is also gone. So now we are at this position, and even now if the consumer asks us what is the min element at this given point of time, we can very easily say that it is 2 because we have access to the top element of the stack and the min value associated with that is 2, and this is also a constant time, so we didn't need to recalculate the min value at this given point of time. So this approach works perfectly fine. Of course, time complexity for this approach is constant, but there is another catch over here. The space complexity of this solution is linear because we are actually doubling the space for each stack implementation. For each value or each element in the stack, we need to store another variable, that is the min value, and this basically doubles the size of our overall stack, and hence if we have n elements, we need n space to store the min values as well. And this is the main drawback with this approach, the space issue. And coming to this point, what I feel is that we can do better, and that is what is being looked at also from you as an expectation for this question. How can you make this better in terms of the space complexity? So that we will see in approach 3. So let's look at approach 3 now. The whole premise behind approach 3 is that we maintain two stacks. One for storing the actual items or actual values which we want to put into our stack. The second stack to maintain the current minimum values of our stack. Let's see it in action. So we want to insert a new element into our stack. We push element 2 into our item stack. We also push it into the min stack because the current min value is 2. There is nothing else in the stack. New element comes in, element 4, we push it on top of the stack. No change to the min stack, because 4 is of course greater than 2, so we don't need to add anything new to the min stack. It can remain as is. Another element comes in, element 1, we push it on top of the stack. Now if you notice, we push another element onto the top of the min stack, because now 1 is smaller than 2, so we have to put that into the min stack. Let's see another element, element 5. We push it on top of the stack, but no change in the min stack, because 1 is still the minimum element. At this point, let's assume that the consumer is asking for the min element. We can very easily say what is the min element by returning the top of the min stack. So element 1 or value 1 is the current min value, and this is done in constant time complexity because we have constant time access to the top of the stack at all points of time. This is a key property of the stack data structure. So there is constant time complexity in this operation. Let's start popping some elements from the item stack. So we pop element 5, no change to the min stack because 1 is still the smallest element, and even today if a consumer comes and asks us for the min element, we can return that in constant time complexity. Let's pop another element, element 1. And now if you see, we pop the element from the item stack, element 1, we also pop it from the min stack. Since element 1 is no longer part of the item stack, it should not be in the min stack as well, right? And now the new min element, if any consumer is asking for that, is the current top element in the min stack, which is element 2 over here. And we can still return the same in constant time complexity. So this is how approach 3 works, and as you can see, the time complexity of this approach is order of 1. We have order of 1 access to the min value at any given point of time. Space complexity is also low as compared to approach 2 because we don't have to store the min value for each item in the stack. So the min stack is potentially much smaller in terms of size as compared to the item stack. For example, in this case, even when we had 4 elements into our item stack, the min stack was only having a size of 2, and this can still remain at the same size even if we have multiple elements coming into the item stack if they are all larger than the min stack. So that way the potential complexity or potential size of the min stack is much lower as compared to the approach 2, and that is the main advantage with approach 3. So that's all there is to solve this problem, and don't worry about the code. As always, I have kept the code in the comment section below. It uses JavaScript to implement such a stack, which also has a minimum stack, but the overall concept remains the same irrespective of the programming language. You can very easily write the same logic in any other programming language using some standard data structures also if you want. But our implementation is available. If you want to check it out, please go ahead. Also, if you liked this video, please subscribe to the channel. Also press the notification button so that you immediately get notified whenever we'll be posting a new video. We are going to cover a lot of such problems in the coming days, which can help us know about these data structures in much more detail. So till then, goodbye. Have a nice day, everyone.